Hello, I'm David, and I'm one of the lecturers in the Maths Learning Support at Adelaide Uni. It's semester 1, 2026. This is a revision seminar for the course called Algebra. I did say when it was, yes. Okay, cool. I'm going to put my document camera on. And I have been given some requests to talk about some things in the later part of the course. So, cool. Just one moment, I'm going to pause the recording because I forgot to look something up. So we're going to be talking Joule spaces. This is going to require me to look at all the definitions, see what they mean, try and process them. It's been a while since I've looked at this, yeah, I'm going to look heavily at the textbook, and I think it's okay for me to share it with the correct attribution. So I'm going to share the textbook, which is Undergraduate Text in Mathematics, Linear Algebra Done Right by Sheldon Axler, which is an open access book by Springer Publisher. This current version I'm looking at, these are the editors and the advisory board, and it's the 4th edition, created in 2024 so far, the 2024 edition. Right, I think I have done my due diligence in citing my sources, but this is the textbook for the course this year, and I'm sure it's a perfectly good textbook, even if whatever course you're doing called Algebra has a different textbook. Okay, you can tell he's opinionated about it by saying it's done right to begin with. I've been told it's pretty good. And there should be some chapters. So I presume it's back here in 6, you say? You know, I'm just going to search for Joule. It's under linear maps. Oh, can I change the scrolling? Right, that's better. Okay. Alright, so I'm going to start here and read some things. I may forget to go back and forth between the paper and the thing on the video, so please feel free to tell me that I've forgotten. Okay, so we have a definition of a linear functional at the beginning of this. So we're going to assume that V is a vector space, I presume. I'm going to get there in a second, just bear with me. V is a vector space on field F, then a linear functional is an element of LVF, which is the linear maps from V to F. Okay. Hello, welcome. Oh, that's the screen sharing that's paused. Okay, and just checking a linear map. Means it'll be something like phi which sends v to f in such a way that phi of v plus w is phi of v plus phi of w, and phi of constant times v is something like that. Seems good to me. Okay, cool. And so that's what a linear functional is. And this group is the group of those things. So I'm presuming that you can have, just as an aside, like this is a definition in the notes of the word linear functional. I'm presuming that this would be linear maps from V to W, presuming. And so F is technically a vector space over F itself, and so that all works out fine. Okay, cool. And then the dual space is the vector space of all the linear functionals. Okay, cool. So V dash is the dual space, which is a vector space of the linear functionals for V. Okay, my first question is, in what sense is it a vector space? Because you'd have to be able to add the things together and multiply them by scalars. So, like, I'm presuming that if you have, I'm just going to call them alpha and beta, which are in the V dashed, then that would mean that alpha is a function that goes from V to F, and beta is also a function that goes from V to F. So what would alpha plus beta be? Sorry? So like that would be like alpha plus beta of like the vector V would be like alpha of V plus beta of V, something like that? And alpha times k alpha of the vector V would be k lots of alpha of V, something like that. Okay. Cool. Like for it to be a vector space, you have to be able to do the things vectors do, which is addition and stuff. Okay. Now, what's that? Yeah, linear maps are like matrices. Sorry, I'm having trouble hearing, so I need to have, and then the rain. I could give you the mic. Okay. Yeah, linear maps are like matrices. If your vectors are like column vectors with coordinates, then a linear map is like a matrix. And so you can add matrices and you can multiply them by scalars. So yeah, that makes sense. Cool. Except for linear functionals, they're like as vectors. Just as an example, if you've got that thing like Rn dashed, then your linear map are like matrices like this. Like if you're going to do 3, be like 5, 7, 9. Like you would have something like, times x, y, z. That's the functional, right? Because a linear map is always a matrix if you've got finite dimensional things, and you have to have a matrix that multiplies columns with 3 coordinates and produces answers with 1 coordinate. And so that's what this would be. And so it turns out that the dual space can be described as vectors, more or less, with the same kind of number of coordinates as the original space. Yeah. So your dual, if it's finite dimensional, your dual space is in fact isomorphic to the original space. Which is probably a theorem that's coming. But just in the vibes here, so yeah, you could have something like, do they use capital letters for these things, or do they use little fives? Okay, cool. Greek letters. So you could have like alpha of x, y, z equals this. That would be an example. And then beta of x, y, z might be like minus 1, 0, 4. And so alpha plus beta of x, y, z would totally just be like 4, 7, 13. Yeah, okay, cool. And so this is hinting at the theorem that's coming. Alright, let's go over to the notes again and have a look. Suppose V is finite dimensional, then V dash is also finite dimensional and the dimension is equal to the dimension. Okay. So that's are the blue ones theorems? Propositions? Okay, anyway. So the dimension of V dashed is equal to the dimension of V, which we just discovered when we did that example. Oh, it's dimension. Huh. Look at that. The dimension of the linear space from V to W is the product of the two dimensions. That makes sense, because it's like matrices that go from one size to the other. Yeah, okay, gotcha. I can't go back, I have to find my thing again. Okay. Let V1 up to Vn be a basis of V, then the dual basis is the, yeah, okay, cool. This I can deal with. So V1 up to Vn is a basis for V. Then the dual basis is a list of functionals in V dashed, so that I don't want to write it that way. What I want to write is, I'm just going to write down what they had, is that phi j v k is 1 if k equals j and 0 if k is not j. So what I want to write is, what that means is that phi 1 of v1 will be 1, but phi 1 of v2 will be 0, and phi 1 of v3 will be 0, etc. But phi 1 of v2 will be 0, but phi 2 of v2, yeah, phi 2 of v1 will be 0, phi 2 of v2 will be 1, phi 2 of v3 will be 0, and so on. That's the idea of what a dual basis is. And so these linear functionals are such that when you do the linear functionals on the basis, you get 1 or 0. So it's a little bit like probably doing the dot product of vectors, because if your original vectors are column vectors and your dual vectors are row vectors, it's kind of like doing a dot product. And the dot product of the row vectors with the matching column vector is 1, and the dot product of the row vector with the non-matching column vector is 0, so they're like orthogonal to the other ones. But they're not vectors, they're functions. Cool. Rightio. Now, bearing with this is just me working through the notes. And so we're going to try and combine this within a product spaces somehow, because the question that I bet you gave me had inner product spaces as well. Okay, so technically if you have a basis, yeah. So once you've got a dual basis, right, so we're gearing up to orthogonal projection here, similar to what was in first year linear algebra. So, so back in first year linear algebra there was this thing where you said, like, you know, if V1 up to Vn is a basis, then for all V in V, V is something times V1 plus something times V2 plus all the way up to something times Vn, right? And the correct answer for what goes in this spot is not always easy to figure out, but if you do have a dual basis, then you can figure it out. Because the correct answer for what goes in this spot is phi of 1 times V. And the correct answer for what goes in this spot is phi of 2 times V. And the correct answer, and so on. So if you want the correct coefficient in your linear combination, then your dual basis will do that for you. Well, because you set it up that way. So if V is like something times V1 up to something times Vn, right, then if I do like phi 1 of V, I'll get A1 times phi 1 of V1 plus blah 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 plus An times phi n of Vn, because linear transformations you can just do that. You can pull out the coefficients and separate them over plus. And look, phi 1, sorry, and phi 1 times Vn, phi 1 of Vn is 0, and phi 1 of Vn minus 1 is 0, and phi 1 of V2 is 0, and phi 1 of V1 is 1. And so it turns out that the correct coefficient in the A1 spot is phi 1 of V. And it works the same with all the other ones. And this is very similar to how orthogonal projection worked in first year linear algebra, where you went, okay, every vector in the orthogonal, in the space you're projecting onto is a combination of the vectors, and all you have to do is, as long as they're orthonormal, you can dot everything with those vectors. So back in first year linear algebra, you wanted to project onto the span of like U1 up to Un, where these were orthonormal. And then you would have like, okay, so the projection of V would be some combination of all of these vectors, and the correct answer was V dot U1 all the way up to V dot Un. They were the correct answers. So that was like, in the past, that was how orthogonal projection worked, and this is very similar, but the action we're doing is doing this functional called phi 1 and up to phi n, as opposed to doing dot products, but dot products will work too. So if if your linear functionals are represented by row vectors, where your original vectors are represented by column vectors, then if you have an orthonormal basis, then the dual basis is the basis you've got, but row vectors instead of column vectors. That's pretty much it. Anyway, okay, cool. And it can be difficult to figure out what they are, but it is totally possible to do. I will just say, I just need a little aside because I just for my own purposes. So classic linear functionals are, let A be in Rn, and then you can say that like f of alpha of vector x is A dot x. That's a perfectly good linear functional. So that's one example. And another example, there's a heap of them on functions. You've got f of x. So f sends r to r as a function. They could be polynomials, they could be anything. And you can have that the function of f that produces that does f of 0 is a linear functional. Because when you add two functions together and then sub in 0, it's the same as subbing in zeros first and then adding. Or you could have you could sub in anything. That would work just as well. The thing that does the derivative of f is a linear functional. The thing that does the derivative and subs something in is a linear functional. The thing that does alpha of f being like f double dash minus 6f plus dash plus f, that's a linear functional. Like, basically there's all these linear functionals you can make that you're used to. The actions that you do to functions that are linear, they're linear functionals. Oh, there's this one which is like the integral from like 0 to 1 of f of x dx, for example. That's a linear functional. The thing is, it just has to be an action that you perform on a function that produces a number, and if when you do the action to the functions first and then add them, and then multiply by a constant, it's the same as when you do the action first and then do addition and multiplication, you get the same answer as if you do addition and multiplication and then do the action on the new function. So yeah, these are all linear functionals. Yeah. Specifically with polynomials, alpha of p being the coefficient of x squared in p, that's a linear functional as well. So these are all perfectly good things you can do to functions that behave like linear transformations. Which is cool. And there are a lot of the classic examples that they use in a course like this to say, hey, it's algebra, so anything that behaves this way you can call it a vector. Yeah. Cool. So theoretically, you could, if you wanted to, now, what is the notation for the polynomials of degree 2? Is it like curly P2R or something? No? No? Just a second. Right, maybe in the examples. No, I think P must be not polynomials, it must be something else, unless it is. Oh, come on. Is a polynomial, that's a set of all the polynomials. What about the ones of particular degree? Oh, yep, I was right. P2R. Okay. Cool, cool, cool. Okay, so this is degree up to 2 with real coefficients. So this thing I could choose as a basis 1 and x squared. That's a perfectly good basis, right? And then I could have all the linear functionals of V. Yep. And it should be possible to come up with the dual basis for this, which is a linear functional that turns it into 1 if it's this and 0 if it's something else, right? So this is going to be called like P1 and P2 and P3. I should be possible to find phi 1 so phi 1 of 1 is supposed to be 1 and phi 1 of x is supposed to be 0 and phi 1 of x squared is supposed to be 0. And so it could be that phi 1 is the constant term. So phi 1 of a polynomial is the constant term of p, which is p of 0, right? When you sub in 0 into a polynomial, you get the constant term. Phi 2 of 1 is supposed to be 0. Phi 2 of x is supposed to be 1. Phi 2 of x squared is supposed to be 1. So this is the second coefficient, like the constant. Yeah. So phi 2 of p is the x coefficient. And this is the general vibe. It's very, I've made it very silly because that's what the phi's do. They are the exact linear functional that tells you the coefficient of that vector. But the x coefficient could be done by doing p dashed of 0, right? And phi 3 of p is the x squared coefficient, and that is p double dashed of 0 divided by 2. So I'm making Taylor series here, basically. So, yeah, and so what that means is that if you want to write a polynomial as a linear combination of 1x and x squared, so what if you had q is like x minus 1 squared for x minus 1 squared, right? Just a random one. Then I would know that phi 1 of q is 4 times 0 minus 1 squared, which is 4. Phi 2 of q is 4 times 2 with 0 subbed in, which is minus 8. And phi 3 of q is the second derivative, which is 4 times 2, which is 8. And so therefore we can rewrite q as a basis of these things, because it would be phi 1 of q times 1 and phi 2 of q times x and phi 3 of q times x squared. What's that? I've got to divide by 2, don't I? Sorry. Thank you. Which is exactly what you get when you expand that out. But that's the point. Like, the point of this is that even if your polynomial looks different, or even if your object in your vector space looks different, you can rewrite it as a linear combination of these things using the dual basis. Yeah. And so essentially, making a Taylor series is rewriting your function as a linear combination of the polynomial basis by using the dual basis of the derivative subbing in 0. Yeah, and one of the points of this course is that a lot of the things that you're familiar with from calculus are in fact linear algebra things. Yeah. Okay, so that's good. I think we're good. I might. And a dual basis is in fact a basis, so that allows us to reasonably call it a basis. Gotta love it. So now we have this thing which is a dual map, which is not the same as this linear functionals thing. So bear with me, this is the tricky bit. Suppose capital T, which is in the linear space from linear, I don't know how to read this aloud, the linear thing from V to W, so the linear transformations from V to W. The dual map is the linear transformation from W back to V. Oh, by using the dual basis. Oh, interesting. I'm just going to write that down. So T is in a linear thing group. I really should look up what it's called. From V to W. Dual map T dashed, which is in the linear space. Oh no, it's not from W back to V. It's from W dashed back to V dashed. Right. Okay, so being a map that goes between W dashed and V dashed, that means it must, things that it acts upon are functions that go from, that are in W dashed. Like, this is W dashed, which takes, and T dashed goes from there to V dashed. But what W dashed itself is, what W dashed itself is functions that go from W to the field, right? And this is functions that go from V to the field. Right. So when you have a function from W to the field, which is called phi, you can create a new function that goes from V to the field, and this is T dashed of phi, right? And there's a way of doing that. Now I know there's a way of getting from V to W via T. Yep. And so look at this. Here we go. I have a way to get from V to F by going T first and then phi. So that entire journey, that is what T dashed of phi is. T dashed of phi is the function that does T first and then phi. So T dashed of phi acted upon something in V, because T dashed is something in V dashed. Like, no. I'm wrong, just a second. Yep. T dashed of phi, if phi is in W dash, T dashed of phi. Wow! So you've got L, W dashed, V dashed. If phi is in here, then T dashed of phi is in here. Because that's what L does, it goes from here to here. And so therefore T dashed of phi is in V dashed. Like is linear of V. So phi is a linear function of W, T dashed of phi is a linear function of V, and so T dashed of phi is a function that acts on things in V, and it will do that by first doing T and then doing phi. That's what this says. Yep. That's going to be slippery to hold on to in my mind. But this picture helps me. So the set of all of these things is what W dashed is. The set of all of these things is what V dashed is. Okay. And so they've written this as T dashed of phi is phi composed with T. But that's what this means. Okay, and I drew a picture of that. Yep. And it really is a linear map from W dash to V dash. Okay. So we may be close to being able to understand the question that you gave me. Maybe not. Wow, this is fabulous stuff. So now, those of you viewing this and you in the room, you can see this is how a mathematician who doesn't necessarily understand anything reads a textbook. I may go back and skip things. So differentiation yep. Suppose phi is a linear functional defined by phi of p is evaluating p at 3, that's what this says. Then d dashed of phi is the linear functional given by p dashed of 3. Okay. This next one's interesting. Like you've got that d is the linear functional, which is the linear, not functional, the linear map, which is differentiation. I just need to draw it just a second. This is the example from page 108 of the book. Okay, here we go. Now I'm going to just move some things around on my screen. Okay, on page 108 of the book, you've got that D sends the polynomials in R to the polynomials in R by D of P is P dash. Why are we not having brackets, you ridiculous man? Sorry. I just want to do the second part of this example. So phi sends PR to R by phi of P is the integral from 0 to 1 of px dx. So we want to know what d dashed of phi is, right? So d dashed of phi is in... Okay, so I just want to draw the picture. So you've got PR and you've got PR again. And D does this. And then you've got phi, which sends that to R. And then you've got D dashed of phi, which goes that way. And so D dashed of phi will be d dashed of phi is a function which acts on PR and produces a number, so it takes a polynomial, right? And it will be phi of d of p. And so that means it will be phi of p dashed, which will be the integral from 0 to 1 of p dashed x dx, which will be px from 0 to 1. Yep, which is P1 minus P0. Right. Okay. Weird. So the dualization of... So the dual of D acted upon the thing that's an integral is the answer. No. Okay. So you just do the thing on the derivative. Okay, gotcha. Sure. It was less interesting looking to me than it did then when I finished than when I started. I still don't understand why I care about that, but that's okay. Okay. Now the reason I was wanting to talk about that is the two questions I pulled we pulled from the textbook / the course. This one's got a dual space in it, and so I wanted to know about dual spaces. And this one did not, so I'm not even up to that yet. But this one does have a dual space in it, and I think we should be able to do this one now. Okay? Because it's got dual spaces in it. So I reckon we can do that problem now with the information we have. We may have to look up a theorem, and so I'm just going to have a quick scroll to see how much space we've got. Oh, an annihilator. Okay, cool, cool, cool. We have some theorems. So the act of dashing a linear transformation is also linear, according to this theorem. And that's interesting. When you dash a linear transformation, which is a product, you reverse them. That's how transpose works. When you transpose a matrix, if you transpose the matrix and then if you multiply and then transpose, it's the same as multiplying the transposes but in the reverse order. So I reckon that this dash thing, this dualizing of a linear transformation, is more or less the equivalent of doing a transpose of your matrix. Because if a linear transformation from V to W is a matrix, then the matching linear transformation from yes, that is exactly what it is. Okay, so I just want to do an example. If you've got the things from like R3 to R2, that's equivalent to matrices, where you have like T of X, Y, Z is like matrix times X, Y, Z, and it'll have, right? Yep, okay. That's what that is. Like it's all the matrices, more or less, that are 3 by 2. At least the linear transformations that go with the 3 by 2 matrices, that's what it is. And so if R3 is column vectors, then R3 dashed is linear transformations made by row vectors, as in, you know, something, something, something times X, Y, Z, right? And if R, same for R2, col vectors, R2 dashed, row vectors, then if you want a transformation that goes from R2 dashed to R3 dashed, you need to multiply your row vectors. Yeah, but because we're seeing these as linear transformations, we have to view them as column vectors. So when we write them as column vectors and we put a matrix next to them, we have to have your write as column vector. We've got something with 2 things in them. We're going to need something like this. It's transpose. Right. Okay. There's probably something else going on as well, but I'm not thinking it through at the moment. I'm just trying to match it up with things that I understand. Yeah, so it is like the extremely fancy. So if you want to talk about matrices without talking about matrices, you have to talk about linear transformations. So if you're going to talk about matrices without talking about matrices and you want to talk about transposes, then what you have to do is do a thing with linear transformations that turns rows into columns, which is dualizing. Yeah, columns into rows. Okay, just thinking it through. This is not necessarily. This is vibes. Just a second. So I just. Yeah. Yep. So yeah, if you'd like a linear transformation made by a row vector, yeah, it's totally the. No, Yep. Yes. So you know that if you wanted a linear transformation that turned a row vector with 2 rows, you'd need it on the other side, right? You can't multiply row vectors by matrices, and so everything's on the other side. And so this is right. And so you would, if it was transposed, you could have the original thing back. Yeah. So it, yes. Okay. So it's technically transposed, but only because you're using your matrix to act on row vectors instead of on column vectors. Yep. So if you would like if you have a matrix like this and you acted on column vectors, then that's great. But if you have the same matrix and you acted on row vectors, it'll do that. That's the idea. This is T, this is T dashed. But it's tradition when you write matrix operations for vector spaces to write all your vectors as columns, which will cause this to be transposed. If your vector, which is a linear transformation itself, yeah. Cool. So technically it is transposed because everything's transposed. Like the other things around them have been transposed. Sweet. I don't think I've ever understood that. I may not quite understand it now, but I feel better. Okay, so we have a problem. Bear with me, I'm just scrolling to, there's annihilators. I choose not to look at that. Oh, null spaces. So I want to get to my inner product spaces eventually, but this is enough, I think. We can talk about null spaces of linear transformations and things, but apparently that's after doing the dual. But doesn't look like it uses. Oh, the dimension of the range of T dashed is the dimension of the range of T. The range of T dash is the null space of the annihilator. Okay, so we'll just deal with that in a minute. I've only got like 45 minutes left, and my plan for this seminar is not to cover everything in these things, but just enough to do this question, and I think we can do the question now. Okay, so my question is this, that I've been given, which is, I believe, in the textbook on page something. This was on page 115. And it's question 15. Okay, so define T, which sends the polynomials on R to the polynomials on R, by T of the polynomial acted upon X is this polynomial. We've done X squared times the polynomial plus P double dashed X. And that is definitely a linear transformation. It takes a polynomial and it produces a polynomial, and if I put P and Q in first, it'll all work out fine. Okay, suppose phi is in the polynomials over R dual, which is the linear functionals that go from polynomials to R, is defined by P dashed of 4. And yep, I wrote earlier that that is one of the kinds of linear functionals on polynomials, so we can definitely do that. Describe the linear functional T dash of phi. Okay, so, pardon me. I'm just going to draw my picture. I'm going to do it, I might do it backwards, so it's okay. So this is T. It goes from polynomials over R to polynomials over R. And then phi sends the polynomials over R to the real numbers. And T dash of phi does this. So T dash of phi is technically a linear functional as well. Okay, so T dash of phi is a linear functional, so it will on PR. And so T dash of phi of P is phi of T of P. And T of P is this. No, I'm not going to do it all in one go. I'm just going to write down what T of P is. So T of P is x squared P of x plus P double dashed x. And phi of anything is what you get when you sub in 4 into the derivative. So T of P is a polynomial, and so when I do the dashed on that, I'll get, based on the chain product rule and things, 2x times P of x plus x squared times P dashed of x plus P triple dashed of x, right? And T P dashed of 4 will be 2 times 4 times P of 4 plus 4 squared times P dashed of 4 plus P triple dashed of 4. Which is 8 times P of 4 plus 16 P dashed of 4 plus P triple dashed of 4. Sure. And this is phi of T of P. Yep. So T dashed of phi of P is this. It's not particularly edifying. Does this book have answers? No. No. Cool. Thank you, Goggle. Okay. I feel like that's right. Like that's what it is. T dashed of phi is phi of t of p. Like t dashed of phi enacted upon the thing that's here is phi of t of that thing, and that is this linear functional. And look, this is pretty stupid, so I'm pretty sure it's not going to be anything nice. Okay. It's not edifying, but that's okay. And part B is, suppose phi is in this dashed and is defined by the integral from 0 to 1 of p. Evaluate t dashed of phi of, damn it, of x cubed. Okay. So just going to draw my picture again. Okay. So, t dashed of phi of x cubed is going to be phi of t of x cubed. Yep. Which is phi of x squared times x cubed plus the second derivative of x cubed, according to what t is. And so that's phi of x to the 5 plus 3x squared and then 6x. Okay? And phi is the integral of that. And so that's the integral from 0 to 1 of x to the 5 plus 6x dx, which is which is 1/6, 3 1/6. So 19/6 if you really want to be all vulgar fraction on us. Yeah, because if we sub in 0. And that's it. So not edifying, but at least it helps us understand what's going on. Like yeah. And what t dash of phi would do to any polynomial is that move. It would do this move and then that move, and it would give you an answer. Sure. So this is the transpose. Like, in some ridiculous sense, t dashed is the transpose of t. Sorry? No, well, no, t dashed of x cubed is a number, but t dashed is an action that you perform on functions to produce new functions. Yeah. So if we chose a basis for everything, then we could conceivably do this with matrices and see the transpose a little more obviously. Because what this does to the basis polynomials will be similar to what it does to the dual bases things, but in a transpose sort of way. But that is all extremely hidden when you're doing things in polynomials. Right. Okay. So yeah, so presumably if we actually went through the effort of looking at the polynomials the basis for things. We could have seen it do things at least for the cubes probably. Okay, sure. Okay, I think that's enough for dual spaces right now. And I've got half an hour and I'm going to make a good attempt on the other bit. Okay, so let's do some inner product spaces. This is the question that I've got here. Which is from somewhere inside the course. It's going to require me to know what... So I know, so far in this question, I know what this means. Technically, I can intuit what the range of a linear transformation is. That would be like the range in an ordinary function sense, the collection of all of the vectors that come out. And I know what dimensions are. It's like how many basis vectors there are. I know, and so singular value decomposition is something that I do not currently know what that means in this context. And I'm possibly a little bit on it even from first year linear algebra. But I can see that a singular value decomposition appears to be, just based on the question itself, even before I go and even naively don't just base it on what is on the page, is that T of a vector in V is a linear combination of these F's. And so these F's have to be vectors because in W, because T of V is in W, because T is in the linear transformations that go from V to W. So these vectors F must be in W. W has dimension 4, so I believe they're a basis for W, is my guess. I'm going to make a guess that these E's, because I've done an inner product of V with E1, these E's are in V. I don't think they are. Because how can you do an inner product of something in V with something in W? But this is an inner product. So I think these E's have to be in V. So these E's are in V. I presume they're a basis too for whatever it is they span, but they're not a basis for the whole of V, because V's got dimension 5. So in some sense this looks like I'm trying to copy a part of W in V in some way, is what I'm thinking. Right, but this does has vibes of this linear functional dual space thing. Yeah. And then there's these numbers here, which would not be surprising to me to be related to the functions that go from E1 to F1. Yeah. So I have thoughts about that. So T3 is a map with the dimension of the range. And then we've got this, somehow this, I would read that with ordinary vectors as the length, but let's say the norm maybe, the norm of T minus S. So somehow I'm able to do T minus S, I'm able to subtract matrices, because that's what these are really, they're matrices, and somehow find a norm for a matrix. So I'm going to need to know how to do that too. But norms are usually made with inner products, so it should be possible. But this is my instinct just reading the question of the things I need to know and what these things are. So I know what I'm looking for when I go looking through the notes. the textbook, as it were. It's getting colder and colder in here. Okay. Water. Right. Let's learn some things. Do you know what? I'm just going to do the singular value and see where I get. Course. Okay, suppose T is in the linear space from V to W, then T star T is a positive operator. The null space of T star T is the null T. What is T star? Of course it is. Ah. The adjoint of T is the function T star, which sends W to V such that T, the inner... Okay. Just a cotton picking minute. Just to be clear, if you've got V and W, that's an inner product. An inner product works exactly the same way as a dot product works. Right? So it's essentially a function that goes to the numbers, to the field. So it should be that sends like V cross V to the field. Something like that. And it should have the property, I'm assuming, that V plus W Z is V Z plus WZ, and that VW is the same as WV, probably, maybe with a star, and KVW is KVW. They're my guesses as to how it should work. VV has to be positive. And only 0 if V is 0. Yep. Oh, F is R or C. Yeah, okay, dot product, cool. Positive, only 0 if V is 0. Additivity in the first slot, homogeneity in the first slot, and conjugate symmetry. Okay, I did that right. I put it as a star, but, you know, whatever. It can be a bar. So if your field is R, then it's just ordinary symmetry, right? In product space, it distresses me with the complex ones that pulling constants out of the first coordinate is different to pulling it out of the second coordinate. I'm distressed by this, but anyway. Just going to write that down as a note to myself. Note if the field is C, first coordinate of inner product. Yeah, come on. Behaves differently to the second one because it works fine for addition for scalar. U lambda v is lambda bar uv. Okay. Rightio. Okay. So, with my inner product spaces, blah blah blah, and then we have a norm is the square root of the inner product with itself. Oh, so that must mean that when you do the inner product with itself, for us to say greater than or equal to 0, that means it must be real. Oh, but that's okay, because when you switch the coordinates, it's supposed to be conjugate of itself, which makes it real. Okay, everything's fine. All right. So it's worth noting, this is one of my favourite things about inner products. In general, inner products are made by multiplying the coordinates together. And one of the classic ones is for functions that thing, the set of functions which sends R to R. You can do, so when you multiply when you do the dot product of two vectors, you know, you multiply the matching bits and you add them up, right? So with functions, you multiply the matching bits and you add them up. And usually you'll do it from like if they go from A to B to R and then you go from A to B. That's the idea. It's like this, the equivalent idea when you're doing dot products. So over in differential equations and Fourier series and stuff, when you do the integrals that are calculating the coefficients of Fourier series, what you are doing is an inner product, because you are trying to write your functions as a linear combination of a basis. Yeah. Okay, you can bring lengths out. Orthogonalness is the same when the dot product's 0. In case you didn't know, ortho means correct and gon means angle. Sorry. Ortho means correct and gon means angle, so it means correct angle or right angle. Correct meaning right. Ortho also means straight, it means straight angle, but that's the 180 degrees, so it's, it means correct angle. But what we've done is we've co-opted. We say, well, sure, we don't have angles anymore technically, but what we do is have a dot product, and dot products used to be 0 when things were at right angles, so we're going to borrow the word. But we're going to use a fancy enough word so it doesn't sound like we're talking about angles. Orthogonal. Yeah. Pythagoras' theorem, if they're orthogonal. This is orthogonal projection, right? Cauchy-Schwarz inequality. I don't think any of that's relevant at the moment. I reckon we can skip to something that's about... Ooh, fun. So what was my issue? I would need to now, and I think maybe I'm ready to now look up singular value. Oh, we needed the adjoint first, didn't we? Okay, so I reckon we can do the adjoint. So the adjoint is the function t star such that that does that thing. Why does it make sense? By the Rees representation theorem. Oh, you can make... Oh... We probably should go back to the Rees representation theorem because that's a big thing with inner products. What's that? If you've got an inner product and you have linear functionals, which were things that were about vector spaces, but your vector space also has an inner product, then you can redefine your inner product. Like you can redefine any linear functional as an inner product. That's what it says. So I'm just going to write it down. So the Rees representation theorem says V is an inner product space and it's finite dimensional. You've got it on this. So given any linear functional phi, which sends V to the field, right? There is a unique U in V so that phi of any V, no crap, I've done it around the wrong way. There is a unique V in V such that phi of any vector u, I'm just going to call it x if that's okay, it's just easier for me to process. Phi of vector x is the dot product of x with v. And it requires you to make an orthonormal basis to do it. But an orthonormal basis is and use the dual probably. Yeah, you're doing Gram-Schmidt basically. But it doesn't, like, knowing that it exists means that you can find it without finding the orthonormal basis. Yeah. So one of the classics is that if you've got your polynomials, you know that, and you've got your inner product of f and g is the integral from like 0 to 1 of fg dx, for example, and you've got your phi of polynomial is like p of 1, then it is actually possible to evaluate every polynomial at 1 by integrating it with another function. And there is a function that will do it. As long, oh, this isn't finite dimensional, so maybe we'll do it with just P2R. It's actually possible to find, so it must be possible, there is a function h so that the integral from 0 to 1 of p x hx dx is p of 1 for every p. Which is just wild. But that's what the Rees representation theorem says. If you have an inner product, then there is a function, and then any function that goes from your vector space to your field can be done as a dot product, which is just, inner product, which is just wild. Like, I'm like, way, hey, what, that's amazing. No, that's really only my second page in this particular section. So, can I understand singular value decomposition yet? We needed an adjoint, didn't we? So, adjoint T is in the thing from V to W. Adjoint T star, which is different from T dash, which sends W back to V. Okay, so i.e. T sends V to W. Has that TVW is VT star W for all V in V and W in W. To see why that makes sense, fix W and W, consider the linear functional which goes from V to the inner product of TV and W. There's a unique vector such that that linear functional is given by taking the inner product, and that unique vector is T star W. No, don't get it. So this is a linear transformation from R3 to R2. So T of this and this, and that's what T is. And then we've expanded out the dot product. And then we've kept those ones. And then this is the function that goes from R2 back to R3. Okay. I really want to write that one matrix-wise. Yes, in a different sense than it was transposed before. Yeah. Yeah. I'm just still gonna write it down. So T sends R3 to R2 by T of x1, x2, x3 is x2 plus 3x3, 2x1, which is this matrix. So the first row has no x1s and 1x2 and 3x3s, and the second one has 2x1s and no x2s and no x3s. It's that matrix. Okay, and so then to compute T star, I shall call this matrix M. So then the inner product, which would be a dot product of T of x, and let's call this Y, is the inner product of mx and y. Ah, yes. Which is like the dot product, right? And if you do matrices, the dot product, you have to write one of them as a row. So when you do a dot product with matrices, like if you have like x dot y and they're both vectors, you have to write one of them as a row and do the matrix multiplication. Like dot product for vectors, and that is x transpose y. Right, so if I do this as dot products, tx dot y is mx dot y, which is mx transpose times y, which is x transpose m transpose times y, which is x transpose dot, which is x dot m transpose y. Oh, it really is the transpose. Oh. Oh. Huh. Huh. But it's the transpose in a whole different way than the other one was, because the other one was about linear functionals. Though technically the Rees representation theorem says that dot products are linear functionals, and so I'm sure it all connects. And I wouldn't be surprised if there's a theorem coming that does it. Okay. Okay, so that's adjoints. So adjoints do what we expect them to do, similar to the dashes. No, can't hear that.
Those are like the rules of dashes.
Yeah, same as the rules of dashes, except a few extra bits and pieces. With this conjugate duva lucky, but that's because we got it from the inner product, which had conjugates in it. Rightio. Dual spaces. So the null space of T star is the range of T perp. Oh yeah, that makes sense. That's just linear. Yep. Okay. The matrix of T star is the conjugate transpose of matrix T, so it's not quite transpose. It's only transpose if you're in real numbers. Gotcha. Yep. So just a second, matrix for T star is matrix for T transpose conjugate. Okay. Yay. All right. So an operator is, yep, gotcha. And then there's eigenvalues, fun times. And we're nearly, here we go. Nope. I was just trying to find the length of a matrix. What's this? Does that mean that it's defined in a whole other spot? What this? Oh no, that's the length of a vector. That's okay. What's the length of an operator then? Sorry? Lemons, so I can hear again. All right. So if something is normal, then its eigenvectors are orthogonal, and normal is where T adjoint T is T adjoint is they are the same. So back in first year linear algebra, if a matrix had real eigenvalues when it was had orthogonal eigenvectors when it was a symmetric matrix, when it was equal to its own transpose, which is something doesn't feel like this. Oh, but self-adjoint is the same as equal to your own transpose. Okay. So this is kind of more general, right? Yep, okay. So normal is, so self-adjoint is inside normal. Like, and normal, which is that T star is T star T, that idea there. They're inside each other. So this one's apparently normal but not self-adjoint. These are exercises. Spectral theorem is eigenvalue things, right? So if it's self-adjoint, and only if, then there's an orthonormal basis that will give it a diagonal. Okay, and singular value decomposition is an attempt to do this, but not for operators, so for things that go from V to W instead of going from... Okay, here we go. So we have some properties of T star T. It's a positive operator, which has a meaning. It has null things. So T star T, just a second, so if T goes from V to W, and T star goes from W back to V, and then T star T, T goes from V to W, T star will go back to V, so therefore it goes from V to V, and therefore it's an operator. Okay. Suppose that singular values are the non-negative square roots of the eigenvalues listed in decreasing order, each included as many times as the dimension of the corresponding eigenspace of T star T. So because T star T is a positive operator, I think that's going to cause it to have eigenvalues that are all positive, and it's also self-adjoint. T star T is self-adjoint because its adjoint is T star, T star T star is T star T star star, which is T star T, so it's self-adjoint. So not only is its eigenvalues all real, its eigenvalues spaces are all the right size, and the eigenspaces for different eigenvalues are orthogonal to each other. So therefore T star T has orthogonal eigenspaces. It has an orthonormal basis of eigenvectors. Right. And so therefore the statement that the singular values are the square roots of the and positive eigenvalues. And so the singular values being the square roots of the non-zero ones included in order of the dimension of the eigenspaces, that'll be fine, right? Because it's all good. Yeah, it'll have all the eigenvalues that it needs to have, and all the missing ones will be zero. It'll be grand. Yeah, and so singular values, the square root of eigenvalues, basically, and include them via multiplicity. Okay, so when you do the singular value decomposition, oh fun, the number of positive singular values is the dimension of the range. So suppose T is, this is what singular value decomposition is. Alright, here we go. I'm going to have to stop in just a minute, but I really wanted to get to this point. What's that? I'm recording the document camera, and it is just in the right space. So T is in LVW. This is the definition of singular value decomposition, by the way. And the singular values... Why does it keep saying positive singular values? Because doesn't it only have positive singular values? because they're the square roots of the square roots of the eigenvalues that aren't 0? Like, why say that?
I think someone else did. And it might be the wrong answer.
Right. The non-negative square roots of the eigenvalues. But, the singular value is allowed to be 0. Right, gotcha. So the positive ones are the not 0 ones. Yep. Thank you. So the singular values are allowed to have zeros. Okay, so the non-zero singular values are S1 up to Sm. Okay, then there exists is orthonormal lists, because they're not a basis for the entire of V1, so they're not calling them a basis. They're a basis for something, but not a basis for... So I was correct at the beginning when I looked at this. These were orthonormal things in V, and these were orthonormal things in W. So that TV is S1 of the inner product of this for all V in V. So I was right that these F's are an orthonormal thing in W. The E's are orthonormal things in V. You're doing dot products with them, and these are the singular values. That was the bit I was missing. And then an FK is T, just as a definition in the proof, FK is T of EK divided by SK. That's useful to know. Yep. All right. That might be enough, other than I don't know what the length means. I don't know what this means. What is the norm of a matrix? But I do understand this now. This means that the singular values of t are 3 and root 2 and 1 on root 2. This I know to be true at this time. And also, I also know, therefore, that those eigenvalues all have separate eigenspaces. Oh, can I go back to that proof and see where the e's came from? The e's were eigenvectors for t star t. See? EK is eigenvector for eigenvalue of t star t, which is sk squared. That one. Okay, so what that means is that these e's are eigenvectors of t star t. Right. And t star t is a linear transformation from v to v. So one of the singular values is therefore 0, because we've only got 4 eigenvectors. But it has to be 0 because we're going to a smaller space anyway. We had to lose something going down to W. Right. Okay. Cool. I really, really wanted to know what the norm of a matrix is. Maybe I can... No. About what?
In terms of like, there's some rule about like the norm of something.
So we've got an upper bound for the length of TV.
Yeah.
Oh, here we go. The norm of... There it is. There's my definition of the norm of a thing. So the norm... it wouldn't have been a norm of a matrix. It would have been the norm of a linear map. Because we don't have matrices. Def norm of T. The norm of T is the maximum value of T of V such that V is in V and the norm of V is less than or equal to 1. Okay, so you make a circle of vectors, or a sphere of vectors, right? So you've got these are all the length of V is less than 1, right? And then you do T of all of those things. T of all of those things, right? And then it's the longest length there. That is the norm of T. Right. Sure. So, what's our theorem now say? T3 is a map such that the dimension of the range of T3 is 3. And I presume that T3 must be in... T3 goes in the spot where S goes, right? So in order to subtract them, they have to both be in VW, right? Three singular. Yeah. So T3 would have to have three singular values because the number of non-zero singular values is the same as the dimension of the range. Yep. Gotcha. So we're nearly there. There's got to be a theorem on the way, but at least I understand what this means. I don't really understand what T minus T3... Oh, no, I do know what that means. Do you have some properties? So we do know that the norm of T minus T3 I'm just going to go back to here. Here are some properties. This, if I have T minus T3 here, and using this one as well, I'll get the length of T plus the length of T3. Not that helps. Oh, amazing! It's the biggest singular value. So the length of T is the biggest singular value. So in our story here, in this thing here, the length of T is definitely 3. Like the norm of T. Right. We're so close to something. Here we go. We've got a theorem. Best approximate by a linear map whose range has dimension less than or equal to whatever we want. Okay. Here's our theorem. Suppose that T is in there and they are positive singular values of T in order. And suppose that K is somewhere between but less than this. The minimum value of the length of that is sk plus 1. Okay. So, wait. Oh, I am so close. So, we have t sends v to w. S1 is more than S2, etc., all the way up to Sm. Alright? And then there's a k somewhere in the middle, from 1 to m. M minus 1, m, and k is in there somewhere. Then the minimum value of the norm of t minus s such that s also sends v to w, and the dimension of the range of s is less than or equal to k, is the k plus 1th thing. So that's saying that the minimum of the ones such that the dimension is less than or equal to 1 is s2. So the minimum t minus s blah 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 dimension is less than or equal to 1 is s2. Blah 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 dimension is less than or equal to 2 is s3. Blah 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 dimension is less than or equal to 3 is s4, etc. Okay. So, and furthermore, if the singular value decomposition is that, also, if TV is S1, V, E1, F1, etc., is the SVD, then and TK happens to be equal to the same thing, S1, V1, E1, F1 up to the K spot, not V1, just V, EK, FK, then the length of T minus TK is SK plus 1, and the dimension of the range of TK is K. Okay, so here's the question. So this is the singular value decomposition. T3 is a map, and it does have this being minimal over all the maps with the dimension of the range of S being 3. Right? Therefore T3 is the ones with dimension of the range being 3, which is this bit. Yeah. According to that theorem. And the length of T3 is the singular value we were up to, which is 1, is the singular value you were up to when you got to that point. And so if we wanted ones with dimension 2, it would be the one of them that has dimension, the range with dimension 2, that has the longest one, the one that's it's the minimum, right? Is it the minimum? Yeah. The closest one to T, with dimension 2 would be this one, and it has length root 2. Yeah. And the closest one to T with dimension 1 is this one, which has length 3. Yeah. So wait, isn't the length of T 3? Is the biggest, or is it the smallest? No, it's the biggest. Yeah. Okay.
So like T3 is 3
So I know, but it doesn't apply all the way up to the same sized one. That doesn't apply. Okay. All right. I think that's what it says.
Yeah, that makes sense.
Right.
Because I'm trying to make T take T3.
Oh, no. It would be this one. Sorry. It's the singular value after where you are.
Yeah.
So it's not 1, it's that one, 1 and root 2. Yeah, it's the one after where you are. Right. So the one that's got dimension 1 would be this function, and that has length root 2. And one with range dimension 2 would be this function, it has length 1. Yeah, like norm 1. Right. Okay. Well, we solved the problem. We got there. We just had to work our way to the theorem that things in between. And this is my problem. When people come to Maths Learning Support in like week 12 of a third year course and say, oh, just help me with this, it's easy. It's like, yeah, but we need to know what these words are. And we look them up. Now we need to know what those words are. Now we need to know what those words are. It's like, this is why you can't just come to us in week 12 of a third year course. If you came every week, we might have learned it along the way, but we did not. But as a person who's in this course, who's seen those things so far, they should all be vaguely familiar, but relearning any of these things usually requires you to chase down the notes all the way back until you can get to the point where you know what the definition means. But it also means, just worthy of note, that a lot of these questions that look really complicated, there's a specific theorem that goes with them. So there you go. Moral of the tale for everyone watching this in the future. All right, see ya. Bye.